Good morning, students. Welcome you again on my second class of class 11. In the last class, means first class of principle of mathematical induction, I solved two questions. I think question number 1 and question number 4. And today I will solve a few more problem from these chapters. Okay. Let's start as I have done up to question number 4. So I am doing question number, suppose question number 7. Question number 7 is that 1 into 3, 3 into 5, 5 into 7, we have to prove up to ... and the last term is 2n minus 1 into 2n plus 1, which will be equal to n into 4n square plus 6n minus 1 by 3. Okay, so we have to prove this one. Okay, so let the given mathematical statement as p of n, and which is equal to 1 into 3 plus 3 into 5 plus 5 into 7 plus ... and the last term is 2n minus 1 into 2n plus 1 which is equal to n into 4n square plus 6n minus 1 by 3. By principle of mathematical induction, we have to prove this one. Okay, so I think you remember the process actually have to apply here. So first we have to check whether the statement is true for n equal to 1 or not. So check that one. So for n equal to 1, what is the value of the expression in the left hand side, which is equal to 1 into 3, and that is equal to 3. And the value of the expression in the right hand side, which is equal to 1 into 4 into 1 square plus 6 into 1 minus 1 by 3, and which is equal to 4 plus 6 minus 1 by 3. So 4 plus 6, 10, 10 minus 1 is 9, and 9 by 3 is equal to 3. So value of the expression in the left hand side 3, and value of the expression on the right hand side is also 3. That means the mathematical statement is true for n equal to 1. Now we'll consider that the given statement is true for n equal to k. Let the statement is true for n equal to k. We are considering it, the statement is true for n equal to k. So as the statement is true for n equal to k, that means p of k, which can be written in the form 1 into 3 plus 3 into 5 plus 5 into 7 plus ... plus 2k minus 1 into 2k plus 1, which is equal to k into 4k square plus 6k minus 1 by 3. 4k square plus 6k minus 1 by 3. So we'll use this condition, condition later. So I am giving it a box. We'll use this condition later. Now we have taken here this condition is true, or the statement is true for n equal to k. Now we'll consider this expression p of k plus 1, which is equal to 1 into 3 plus 3 into 5 plus ... and the last term will be if I put k equal to k plus 1, or here n equal to k plus 1, so the result will be 2k plus 1 into 2k plus 3. 2k plus 1 into 2k plus 3. You can check it by putting n equal to k plus 1 in the last term of this expression. Okay, now we are rewriting the equation. We have 1 into 3, second term is 3 into 5 plus dot 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 dot, and the last term is 2k plus 1 into 2k plus 3. And what is the previous term of the last term? And that is, which is this, means 2k plus 1, 2k minus 1 into 2k plus 1. Now look at this expression. Value of this expression is given here, k into 4k square plus 6k minus 1 by 3. So put it here. So that is k into 4k square plus 6k minus 1 by 3 plus 2k plus 1 into 2k plus 3. 2k plus 1 into 2k plus 3. Now just do the LCM. Okay, I am rubbing this portion due to shortage of space. Okay, so first do the LCM. So it will be k into 4k square plus 6k minus 1 plus 3 into 2k plus 1 into 2k plus 3 by 3. Now multiply this one, means multiply the whole thing. So it will be 4k cube plus 6k square minus k, and if I multiply this, so it will be 3 into, first multiply these two bracket, so it will be 4k square plus 3 to the 6 plus 2, 8k plus 3 by 3. And now multiply the expression, multiply it by 3 again. So this is equal to 4k cube plus 6k square minus k plus 12k square plus 3 8s are 24k plus 9 by 3. Do few more step, that is 4k cube plus 16k square plus 12k square, that is equal to 18k square, and this is 24k and minus k, that is plus 23k, that is equal to plus 23k, and a plus 9 by 3. Look, 4k square plus 4k cube plus 18k square plus 23k plus 9. Now we have to factorize this expression. I am factorize this expression here. 4k cube plus 18k square plus 23k plus 9. Now look, the given expression is vanished if I put k equal to minus 1. Put k equal to minus 1. So 4 into minus 1 whole cube plus 18 into minus 1 whole square plus 23 into minus 1 plus 9, which is equal to minus 4 plus 18 minus 23 plus 9. So that is minus 4 and minus 23, that is minus 27, and 18 plus 9 is 27, that is equal to 0. So since the expression is vanished for k equal to minus 1, so factor of the expression is k plus 1. Okay, so write k plus 1, k plus 1, k plus 1. Okay, so as it is 4k cube, so put 4k square, that is 4k cube plus 4k square, and it is 18k square, 4k square, so put 14k, so plus 14k square plus 14k and plus 9k plus 9, so that is equal to k plus 1 in one bracket, and write the k square plus 14k plus 9 in another bracket. So this expression can be written in the form k plus 1 into 4k square plus 14k plus 9, 4k square plus 14k plus 9. Now look, we have to do little more calculation here. Okay, so last line is 4k square plus 14k plus 9, means we have to proceed with this exam, 4k square plus 14k plus 9. Okay, so we are rewriting the equation, that is 4k square. Now 14k can be written in the form 8k plus 6k, and 9 can be written in the form 9k can be written in the form as 9 means 4 plus 6 minus 1. See, can 9 we can represent 9 like that, 4 plus 6 minus 1. Now 4k square plus 8k and this 4 right together, and 6k and 6, this 2 and minus 1 is here. So if I take 4 common from the first 3 term, so it will be k square plus 2k plus 1, and from the second to next 2 term take 6 common, so k plus 1 and minus 1, so that is 4 into this expression is actually k plus 1 whole square, and this is 6 into k plus 1 minus 1. So this expression can also be written in the form k plus 1 into 4 into k plus 1 whole square plus 6 into k plus 1 minus 1 by 3. So finally we have done. So p of k plus 1 can be expressed in the form that, which is of the form n into 4n square plus 6n minus 1 by 3 for n equal to k plus 1. That means the statement is true for n equal to k plus 1 also. That means by method of induction we can say that the statement is true for all values of k. Okay, the calculation is little bit hard compared to the previous ones. Okay, so have a look here. Okay, so question number 7 is done. Now we proceed to question number 10. Okay, so now we'll solve the next question, question number 10. Now question number 10 is, we have to prove 1 by 2 into 5 plus 1 by 5 into 7, sorry, 5 into 8 plus 1 by 8 into 11, 8 into 11 plus dot 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 plus 1 by 3n minus 1 into 3n plus 2 is equal to n by 6n plus 4. we have to prove that this is equal to this expression, value of this expression is equal to n by 6n plus 4. So as before, first we'll consider this expression as Pn, P of n equal to this expression. Now we'll check whether the expression is true for n equal to 1 or not. So for n equal to 1, see what happened, the left hand side will be 1 by 2 into 5, that is equal to 1 by 10, and the value of the right hand side expression is 1 by 6 into 1 plus 4, and that is equal to 1 by 10. That means the value of the left hand side and the value of the right hand side are equal. So we can say that the statement is true for n equal to 1. Now we'll consider that the statement is true for n equal to k. Let the statement is true for n equal to k, where k is an arbitrary natural number. So as the statement is true for n equal to k, that means p of k can be written in the form 1 by 2 into 5 plus 1 by 5 into 8 plus dot 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 plus 1 by here it will be 3k minus 1 into 3k plus 2, which is equal to k by 6k plus 4. Okay, later on we'll use this line. This is the key line. Okay, we use this line, this condition later, so that's why I given a star mark here. Now next step is we have to consider this expression p of k plus 1. That means sum of first k plus 1 term of this expression. So 1 by 2 into 5 plus 1 by 5 into 8 plus dot 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 1 by, now look, if I put n equal to k plus 1 on the last term, so the last term will be 3 into k plus 1 minus 1 into 3 into k plus 1 plus 2. That means 1 by, if I calculate it, it will be 3k plus 2 and it will be 3k plus 5. So that will be the last term of the expression when we put n equal to k plus 1. So 3k plus 2 into 3k plus 5. So we'll rewrite the line again with its previous term also. So 1 by 2 into 5 plus 1 by 5 into 8 plus dot dot dot. What is the previous term of this term? 1 by 3k minus 1 into 3k plus 2 plus this last term 1 by 3k plus 2 into 3k plus 5. Now do the calculation. Now from here to here, the value of the expression is known here. I have given a star mark here. I told you we have to use this this condition. So if I put this value here, so k upon 6k plus 4 plus the last term 1 by 3k plus 2 into 3k plus 5. Okay, so now so from this, okay, so we rewrite it again. So k by, look from here we can take 2 common. So if I take 2 common, so it will be 3k plus 2 and the last term is here 1 by 3k plus 2 into 3k plus 5. Now look, we can take 3k plus 2 common. So that is 1 by 3k plus 2 into k by 2 plus 1 by 3k plus 5. Add it. So 1 by 3k plus 2 into, if I add, the LCM will be 2 into 3k plus 5, and it will be 3k square plus 5k plus 2. Now if I factorize this expression, 3k square plus 5k plus 2, so it will be equal to 1 by 3k plus 2 into, it will be 3k plus 2 into k plus 1. If we factorize this expression, you have this 3k plus 2 into 3k plus 1 into 2 into 3k plus 5. Now look, this 3k plus 2 and this 3k plus 2 will cancel each other. Then the remaining part is k plus 1 by, if I multiply this one, so 2 3s are 6k plus 5 2s are 10, which can be rearranged like that: k plus 1 into 6k plus 6 plus 4. 6k plus 6 plus 4 means we have to write the expression like this form. So that is equal to k plus 1. If I take 6 common from the first two terms, so it will be 6 into k plus 1 plus 4. Now you can see that this expression is looking like this expression when we put n equal to k plus 1. That means the statement is true for k plus 1 also. So as the statement is true for n equal to 1 and for n equal to k, if we consider the statement is true, then we can prove that the statement is true for n equal to k plus 1 also. Then by principle of mathematical induction, we can say that the statement is true for all values of n. Understand? Okay, I hope you understand. Okay, so okay, I'm doing one more question. Question number 13. Question number 13. Okay, as all the problem are exact, means approximately same type of problem, so I am skipping few problem for you. You try to solve it at your home. So here question number 13 is, we have to prove 1 plus 3 by 1, 1 plus 5 by 4, 1 plus 7 by 9 into dot 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 1 plus 2n plus 1 by n square, which is equal to n plus 1 whole square, n plus 1 whole square. We have to prove this. So first we'll consider the expression, let p of n equal to this. Now we'll check whether the statement is true for n equal to 1 or not. So for n equal to 1, the left hand side will be 1 plus 3 by 1 on the first term, which is equal to 4, and the right hand side is 1 plus 1 whole square, right hand side, which is equal to 4 again. That means the statement is true for n equal to 1. Next step, we'll consider the statement is true for n equal to k. Let the statement is true for n equal to k, where k is any arbitrary natural number. So as the statement is true for n equal to k, then p of k means product of first k term of the expression 1 plus 2k plus 1 by k square will be equal to k plus 1 whole square. This is a very important line. We will have to use this condition later. So this is p of k plus 1. Now we will consider the next, this expression p of k plus 1 means 1 plus 3 by 1, 1 plus 5 by 4 dot 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 1 plus 2k plus 3 by k plus 1 whole square. If I put n equal to k plus 1, so last term will be that. Now we rewrite the last line again with its previous term, writing its previous term. So it will be 1 plus 3 by 1, 1 plus 5 by 4 dot dot dot. The previous term of this term will be 1 plus 2k plus 1 by k square into 1 plus 2k plus 3 by k plus 1 whole square. Okay, now the expression, the value of the expression up to this is known here. It's k plus 1 whole square. So put it here. So k plus 1 whole square into, just add them. LCM is k plus 1 whole square, and it will be k plus 1 whole square plus 2k plus 3. I'm using this portion. Okay, so look, this k plus 1 whole square and this k plus 1 whole square will cancel each other, and the remaining term will be that k plus 1 whole square plus 2k plus 3. That means if I expand this expression with the formula a plus b whole square, so it will be k square plus 2k plus 1 plus 2k plus 3. That means k square and this 2k and this 2k together gives 4k, and 1 plus 3 will gives 4. Now this is a simple formula of k plus 2 whole square, that is k plus 2 whole square. Now k plus 2 can be written in the form k plus 1 whole square plus 1, sorry, k plus 1 plus 1 whole square. Means we have to express the expression like that. So this expression and this expression are same when n equal to k plus 1. That means the value of the expression for n equal to k plus 1 is true. Therefore, by principle of mathematical induction, we can say that the given statement is true for n equal to for all n belongs to natural number. For all n belongs to natural number, and hence true. So this is question number 13. Okay, so next day we'll solve the remaining problem. There are few problems here. Next day we'll solve them. Okay, so if you try, you can solve it up to question number 17, and from question number 18 the process is a little bit different, but you can solve up to question number 17 using the same procedure. So must try it at your home. Okay, next day we'll start from question number 18 onwards. Okay, so let's see you next day. Thank you.